Oh, so many good things are happening today. So many good things. You excited? First of all, we talk about phase today. We talk about phase. And you're going to have an amateur radio licensing exam today. You're going to be a licensed operators next week. Is that exciting? No, it's not open. This one's not open for everybody. Yep. You can't take it more than once, actually. They won't let you.
No, but in a standard...
in a standard, you could, but it's just too many people. Yeah. Okay. So if you fail, you lose the comfort of doing this in class, but you could do it anywhere else. Oh boy, I'm late. You know what it means? This is a positive group delay. That's what it means, folks. It's not a joke, it's a real thing. There are such thing as positive group delays. So excited. Okay, so Jun, any announcement? No. Okay. Welcome, EE123, lecture 23, phase response. Woo! So, a few announcements that I have today. You have the amateur radio exam. Please come prepared. Practice. Who's going to take more than the technician class? Nice. Well, practice as much as you can before. It actually helps. It does help to practice before. So, next thing that I wanted to talk about is announcement. Oh yeah, Friday I'm going to talk about the projects. Okay, so it's something for you to think of while you're, going to Mexico on spring break or something like this. Right, that's what they are. Okay. Phase response. Last time we talked about the phase response. Phase is this elusive thing. This is this concept that, people don't get it till they get it. And most people, like a lot of people, actually don't get it ever. So hopefully every one of you will understand what phase is. And as a person that deals with phase on a daily basis, really appreciate the notion of phase. And phase are basically creating certain delays. And we talked about the system, which is just h e to j omega is a complex exponential, which means that it's a linear phase. It's a linear phase with omega with some coefficients n sub d. And that translates into a impulse response system, which is just a pure delay. Okay. This is just a pure delay. So its frequency, magnitude frequency response is 1. And often when we display filters, we display the magnitude of response, completely ignoring the phase. I mean, what's with that? The reason is that a lot of those are linear phase systems, which only cause, the same group delay. So all the entire whatever response is uniformly being delayed. And so that's not necessarily an issue. But if we're talking about IIR filters, they have a nonlinear phase response, which are going to have some consequences. And last time we talked about the notion of group delay, which is the derivative, the negative derivative of the phase with respect to frequency. And that's the negative derivative of the phase, the unwrapped phase, not the wrapped phase, because we're going to ignore any changes that are, jump that are the order of 2 pi. Okay? So the unwrapped phase. If you take the derivative of this, if this is the phase response of a particular system, what we can think of the derivative is really what a narrowband pulse at that particular frequency, what kind of linear phase it will see. What kind of slope in the phase it is observing, and once it observes it, it's going to be delayed by that amount. Okay, so a narrowband pulse at around omega 1 will actually see a linear phase, which is that much, which is much, so the group delay is much more significant than the linear phase that a pulse around omega 2 would see. And hence, a pulse at omega 1 that is lower frequency would be delayed more after going through the system than a pulse that is at omega 2. And what if you have then an impulse that goes into that system? The impulse is obviously going to be spread, okay? Because different frequencies are going to be spread differently. I mentioned this is, for example, what happens in a lens system or an optical system when you put light and you see colors coming out. And that's because these are separated, then the frequencies are basically separated. Each one of them is delayed differently. If you look at lenses in your camera, sometimes if you have a really nice, not so nice, but really high magnification zoom lens, you'll see some aberrations in the color because of these sorts of delays. Okay? But that, of course, happens with audio. It happens with other systems too. Yep. No, not really. This is not the scale that things are actually happening in MR. MR is observed using radio frequencies, and the distances are so short that this is not observable, this effect. But yeah, I mean the speed of light, changes at different materials, but also for different frequencies. Okay, so RF will propagate at different frequencies than light will propagate through some medium. And so what will happen would be some sort of a dispersion, some sort of a delay. Okay. So this is interesting because what is happening here, that things might scramble, like not being attenuated, but might scramble in space. So let's look a little bit of the math. We're analyzing, again, LTI systems, which have a form of a rational. What do you call these? Rational transfer functions. Sorry, I'm just transfer functions. Rational transfer functions. Basically, if you look, this is a polynomial, which is roots are ck, which are the zeros of the system. This is another polynomial, which its roots are the poles of that system. And if you look at the phase of this argument, what you see is that the phase will add and subtract. It's actually obvious because if you look at how phase is translated into when you take the log, when you have something that multiplies, phase will actually add. Okay? So the phase of the corresponding to each one of these zeros is going to have a certain value, and they're just going to add in negative case here, and the bottom they'll add in the positive. The group delay is a derivative of the phase, hence they still add and subtract. So the contribution for each one of these poles is additive in the phase. Okay, you have a particular phase response for a 0 or a pole, and their response just adds. So that means that if we just analyze a first-order system or a second-order system, any order system can be decomposed into a first and second-order systems. Hence, that's enough to figure out what is the phase response. Okay? Okay. So the group delay then also adds, and if you want to look at the group delay of a particular frequency response, we're going to look at each one of these factors. And we're going to look at either CK or DK, and the difference between them is just going to be the whether it's positive or a negative effect. Okay. If you look at the what is the phase of this argument of this argument, you'll see that it's actually, you can derive it to be the inverse tangent of r sine W minus theta 1 minus r cos sine W minus theta. It's easy to derive in this, and I'll show you actually how you can actually look at from a zero pole point of view. If you take the derivative of this inverse tangents, then you get the following result. This is basically the expression that's easier to derive just from just simple linear algebra. But if you look at the geometric interpretation, this is what makes it a little bit more interesting. If you look from a geometric interpretation, if you look at the argument of 1 minus r e minus j omega, you can also write it as the argument, and pay attention here. What I'm going to do is I'm going to take e minus j omega out as a factor, and then I've got e j omega minus r, all that multiplied by e minus j omega. The argument of that gives me e to j omega minus r, minus the argument of e to j omega. The argument of e to j omega is, of course, omega. And we need to figure out what is this e j omega minus r, and what this actually means from a geometrical point of view. So let's see. If this we call, this is omega, and this we can call phi, what is really omega? Omega is the angle between where we want to evaluate the phase response, right? Where is the phase response with respect to the real axis? What is this angle? Okay, so this is really the frequency that we're going to be along the unit circle. Okay, so it goes from minus pi to pi, of course. Omega goes from minus pi to pi, and those correspond to digital frequencies. Okay, that's great. Now, what is the phase of e to j omega minus r? Okay, so e to j omega minus r is this vector. And so the phase of it is going to be this one. Okay. So if you take now the phase of that minus the phase of this by the angles on a triangle, you can figure out that this angle here corresponds to basically this angle. Okay. And this is interesting then, because what you do then is basically you hold kind of a pin, and with rubber strings, okay, at the point of frequency that you want, and you pin one of those strings into where the polar zero is, and then you pin the other one to the center of the circle, and then you look at the angle between these strings as you move around on the unit circle. This is effectively the phase response of a single pole or zero. Okay? Hence, if we start at 0 and we had a pole at this point, or 0 at this point, then the angle would be 0. right? Because those lines would just overlap. If we stand on the other side, which is pi, they'll also be 0. The phase will, or the angle would increase as we then move along the unit circle. And at some point, it has to decrease in order to cross back 0. And this is exactly that shape over here. And then, of course, as we go the other side, it becomes symmetric if the pole is actually on the real axis. If it's not on the real axis, this is just rotated, basically circularly shifted. Okay? So any pole that is going to be at another position, you just circularly shift this graph, okay, based off what the angle is. But you can maintain all the symmetry because I can just rotate the axes and it would look exactly the same. Does this make sense? So this is the phase response. And this is kind of an intuitive way or geometric way to interpret what would be the response. And of course, as R would be, as the pole or 0 would be closer to the center, then the effect is going to be more smooth. And as it's going to move closer to the unit circle, the effect is going to be more enhanced. Okay, this is these transitions are going to be either sharper or smoother based on how far this is from the unit circle. Okay? Any questions? Now, what does this actually mean? This is not so useful in the sense that, what is really a phase response? Well, a phase response really is that if you put a pure tone, you will come out with a different phase. Okay? That's what it means. You put a pure tone, it will come out with a different phase out of that system. What is the phase that's going to come out of the system? It's the phase response. Okay? But we're interested not just in a pure tone. We look at signals which have kind of a combination of lots of things. But so what we'd like to see, what it was really actually good to see, is the response of what was the group delay, which is the derivative of this curve. And so the faster this change, the group delay is going to be more significant. That means that if I look at the group delay, I see that here it's pretty much linear, almost linear. It's not exactly linear, but it's almost linear, and it's positive. The group delay then is the negative derivative of the phase. Hence, this would be the group delay. Okay. So it's up to here. It starts kind of like negative, and it's pretty much constant for a certain time. Then now there's kind of a switch. The derivative changes from being positive to being negative. The group delay has a negative sign with respect to the derivative, hence it switches from negative to positive through a smooth curve. And that switch is going to be more radical when the zeros or poles are going to be closer to the unit circle. Okay? Then it switches, and then it goes almost linear. It's not linear, but it's almost linear for a while, and then it switches again. Yeah. Here? Okay, so let's say you start at this point, and you put your rubber, how do you call these? Rubber bands? No, it's not bands. Bands like some, rubber strings. And then you move it, right? So it has to increase. The angle increases, so it has to be positive.
But then the negative derivative is
Negative derivative, yeah. What about it? Well, on this port is the derivative is almost constant, so it's constant a little bit. This is a drawing again; it's approximate. And then when it reaches this point, the derivative becomes, negative. That means that you have to jump it, but then phase is continuous, so there has to be some continuum here. Okay. If theta, which is really the phase of this polar 0 is non-zero, then you just shift the whole curve by pi. Okay? So this is the case when we look at this point. If you look at those curves, then you get this point. As you move in, you get to some inflection point, which is, I guess, at this point where the angle becomes maximum. And then the angle then decreases till back to 0. Okay? So that's basically the idea. So frequencies, which would be then low frequencies, would be then, in this case, advanced. Depending on if it's a pole or a 0, it will either be advanced or be delayed. And yeah, and here they'll have again a certain delay. Okay, so it depends on what frequency your pulse is either going to advance, delay, and so on and so forth. So the idea is that when you have poles, they increase the magnitude, but introduce a lot of phase lag and group delay when you do this. So when you put a pole next to the unit circle, it will give you a gain at that particular frequency, but also introduce this large group delay. And the group delay is going to increase the closer the poles get to the unit circle. And the reason for this is that this inflection point is going to be sharper and sharper. And with sharper and sharper means that the derivative is going to be larger. Okay? That's what it means. I just really wanted to go through this animation again. Zeros do exactly the opposite in the sense that they reduce the magnitude and they create the opposite response of a group. Like the group delay would be basically negative group delay. Okay, so things would basically be advanced. So these effects are really more marked when the pole gets closer or the 0 gets to the unit circle. So if you look at a system with a I think this is a 0 at I made new slides last time, and this is from a different thing. So I'm just going to get the just give me 1 second. Let me pull off the slides from last time. Notes. This is last time's material. I just wanted to go through the animation again. Okay. So this is the case when we move the 0. This is a system with 1 0. And the 0 is at negative pi. But R will vary between 0.5, 0.7, 0.9, and 1. So the 0 moves from here to here to here to here, okay, on the unit circle. And as this 0 moves into closer to the unit circle, then you see that the magnitude or the log magnitude becomes, the dip becomes deeper and deeper and deeper. And of course, if you've got a 0 exactly on the unit circle, then that function is going to be 0 at that point, because that's the definition of a 0. Okay? The function is going to be 0. If you look at the phase, the closer, and this is actually an interesting thing that happens, the closer it gets again to the unit circle, the phase will kind of become more sharper and sharper and sharper till it reaches 0, and then there's going to be a jump of pi. A complete discontinuity of the phase. What? A discontinuity of the phase? How can that be? Well, change of sign is a discontinuity of pi in the phase. So it's not really a discontinuity in some sense, right? If you account for the fact that the function just changes sign. Okay? So it reaches this point, and then you've got this discontinuity. So what you have then is a case where the group delay, in that case, would become more and more enhanced as you reach. As the 0 gets close to the unit circle. Here's another example of a second-order IIR system. poles and zeros. There's no zeros here. It's only poles close to the unit circle. And in that case, you see that the magnitude increases as it gets closer to, as the frequency gets closer to these poles, the magnitude increases. It's going to be then the lowest at pi. If you look at the phase, you're going to get, of course, significant effects where you get closer to the poles, but the shape is very, very similar. So this is the contribution of 2, remember? So it's the same shape that you saw before, but only added together, okay, with a shifted version. So that's the nice thing about phase response. It adds in the frequency. And then if you look at the group delay, there is a significant delay that happens at those frequencies. Okay. Here's an example of a third-order system. Third-order system where you have a 0 at minus pi, and 2 zeros over here, then 3 over here. This is what kind of a filter is this? Yeah, but is it a high pass, low pass? What? What do you mean? It's a high pass. It's a low pass. Right? It's a low pass. It's not lowish. It's a beautiful low pass filter. Look at the log. This is the log. Okay? Log. That's 100 factor over here. Okay? Yeah? So this is a log. Okay? So log magnitude. And so you see that close to the poles, there's some ripple. Which actually cannot be a Butterworth filter, okay, because it's non-monotonic. Okay, so you see ripple in the passband. Okay. It could be it's not a shabby. It's not even a Chebyshev. It's just a filter. Okay. There's a ripple here because as you move closer to the poles, it dips down a little bit, it goes up again, and then down to the 0. Okay. And then, of course, when it reaches pi, then it becomes a 0. If you look at the phase response, this is the phase that includes phase wraps. So the phase actually goes negative. It would, if we unwrap it, means that the whole curve will go down. Okay. Means that the whole curve will go down. Okay. And you see this jump just because phase is periodic. If you look at the group delay is on the derivative of the phase without the those phase jumps. Then you see that, first of all, you can see that this system is obviously causal. Yep. And the group delay is positive for all frequencies. It is actually possible to have a negative group delay in a causal filter, by the way. But it cannot be negative group delay for all frequencies. It could be like very singular for one particular frequency. Now I'm going to post a note about, why is that the case. It's really kind of like linear prediction in some way, but it's not really predicting the future. So there's a really nice note that I'm going to post. If you're interested, I'm happy to discuss this in office art. Okay. So now we know how to at least look at what will be the phase response. Phase response is add. We know what the contribution of a single pole and a single 0 to the phase response, which is quite helpful in terms of analyzing what will be the phase response of our system. Now I'm going to talk about several types of systems which are quite useful to analyze. The first one of this class is going to be the all-pass system. An all-pass system is going to be a system that passes all frequencies. So what about just a pure delay? Is that an all-pass system? A pure delay is absolutely an all-pass system. How about a system with constant magnitude response, but some nonlinear phase response. Is that an all-pass system? Yeah, it does because it passes all the frequencies, but it might delay them differently or put a phase to them. The next one we're going to talk afterwards is a minimum phase system and then linear phase systems. Okay, those will be the next. And these are, again, quite useful systems to design and analyze. So here's the definition of an all-pass system. This is my handwriting. Okay, so if you look at the magnitude response of a system in which the poles, the zero is at 1 over conjugate position of the pole. In that case, the system is going to look like this, zeta minus 1 minus A conjugate, divided by 1 minus A zeta minus 1. So the 0 is at 1 over A conjugate position of the pole. If the pole is at A, the 0 is at 1 over A conjugate. And it becomes unstable. But sure. But what is the okay? But then you have to define. Okay, so if you want to look at the magnitude response, you can only do that if the region of convergence is including the unit circle. So we're going to talk about non-causal system. Okay, that's fine. Then it will be a stable system. Okay. But what is the magnitude response of this? Okay, let's stare at this. Let's just take the magnitude. We take the magnitude of this, and then we start, massaging this equation. We're going to look at E minus j omega E minus j omega minus A star divided by 1 minus A, E j omega, and so on and so forth. I can take E minus j omega out. The reason I'm doing this, I want this to look kind of similar. I want to move them in a way that it's easy to analyze. I take E minus j omega out. I have 1 minus A conjugate E j omega, and here minus A E minus j omega. If you look at the magnitude of this is exactly the same as if I didn't have this E minus j omega. So it's really equivalent to the magnitude of this divided by the magnitude of this. This is really, if you look at this is A star E to j omega, and this is the same as A star E to j omega, only conjugate. Okay, so that will give you this. So the effect here is that you have a situation where what is really the magnitude response? The magnitude response for here will be 1 for all omegas. Okay, that's great. That means that if I have this type of a setup of zeros and poles, the magnitude, the amplification given by the pole is balanced by the attenuation given by the zero. That's basically what it means. That would have been also true if the poles and the zero were exactly the same point, which means that they would actually cancel. But here they don't cancel. They cancel the magnitude effect, but they don't cancel the phase effect. And that is the big deal. Because this filter is going to have a phase effect, but it's not going to have a magnitude effect. Phase response. So a general all-pass system is going to look something like that. Okay? It's going to look something like this, where you have real zeros and poles that are at 1 over the position of the pole. And you've got to get also complex poles and zeros, which then, in those cases, the zeros and poles are at 1 over conjugate position. Okay? So if dk's are the real poles, ek's are the complex poles, if with the conjugate E sub k's, And so if I have a pole over here, I should have 1 over conjugate at this position, which is a 0. If I have one here, I'm going to have another one at 1 over conjugate position, which is over here. Okay? So if you just calculate them, you see that this is basically position is being flipped from here to here by 1 over conjugate. Okay? And this one, you just need to take 1 over it, because it's real. Its conjugate is exactly the same. So when you have this setup of a zero pole system where poles and zeros cancel their magnitude effect, but now the phase response is the next thing we're going to analyze. So if you look now at the phase response of this pair of zero pole, you're going to have effectively E minus j omega minus R E minus j theta, which is really A conjugate. And here you're going to get A. What I'm going to do now is I'm going to take E minus j omega outside of this. And I'm going to do the same trick that I've done before, where now I separate. This is multiplying this, so I can take it out. The argument of this is really minus omega. Okay. And then I'm going to take minus twice the argument of this. Why? Because these are exactly the same, okay, except that this is negative and this is positive. But when I look at the phase of this, it's kind of like negative minus positive, you get twice that value. Yeah. Which one? Here? No, because I took it, I multiply, I basically, oh yeah. I think you're right. Is that correct? I think you're... Okay, what I really should have done probably is taking the plus j omega here. No. Twice. Let's see. Huh. Thank you. That's great. Okay, let's see. We take E minus j omega. Then this is 1 minus, yes, E minus j omega R. Fantastic. The phase of this is let me think about it. So phase response of a single pole is the angle between these two. If I have a pole at this point, a 0 at this point, then at at 1 over conjugate what am I doing wrong here? E minus j omega minus a conjugate 1 minus a conjugate here. That corresponds to E minus j conjugate R minus j let me think about it. I just don't want to spend the rest of it. Let me think about it, and I'll post it. I'm not going to spend the next 10 minutes on this right now. My point was, though, is that I'll show you that these actually contribute exactly the same phase. I'll convince you that it does. In that case, the group delay is going to add in the same way. Okay. I'll get back to you on this. But the point of all of this is that the effect of the phase response is actually going to be doubled at those points of inflection, where at the frequency where they're close to these poles and zeros. The zero at this side is going to contribute exactly the same phase response as the pole at this position. And so their phase response is just going to be doubled, as if there were two poles at this position. Okay. The result of a phase here would be exactly the same as if, in terms of its effect, as if there were actually two poles or two zeros at this position. But now their magnitude is basically canceling each other. So the phase response is still significant, but the magnitude response is not. Hence, the group delay for these frequencies is going to be is not going to be now linear. It's not going to be constant. There's going to be a group delay that's going to be also significant close to these poles. And that means that now you've got significant delay that's happening at those points. Now, why would you want to do this? You want to do this maybe because you have a system that has a certain phase response, and you want to be able to compensate, put things back together. So here's a thing that they do in optics, for example. You put a really narrow pulse through an optical fiber. The fiber has certain nonlinear group delay so basically there's dispersion. Different frequencies will be delayed differently, and so that pulse after a while starts spreading till it almost gone in amplitude. Now, is that a good thing? Actually, it's a great thing. It's a great thing because optical systems are nonlinear when you talk about large amplitudes. The response is actually nonlinear inside the glass. And so if you can maintain lower amplitude, then you are still kept in the linear regime. And so this dispersion actually is advantageous. Then what they do is at the end is they put the light that comes out into a grating. That grating effectively creates a spread of frequencies. It's kind of like computing the Fourier transform. And then they're going to put a different delay for each one of those frequencies that compensate for that effect. And then they put it all back through a lens or something like this, and then the pulse comes back out. The pulse just comes back out because all the frequencies add coherently. This can also happen when you're thinking about a communication system where you've got multiple paths through the or different attenuations through the atmospheric conditions. Different frequencies are delayed differently, and then you can compensate for this by applying an all-pass filter. Same thing happens, propagations of sound through water. Different temperature will delay things differently, and so you can use these all-pass systems to compensate for the distortions that happen. And again, sometimes it's also advantageous because if I want to send something through a system and I want it to be linear, if I can reduce the amplitude of whatever I'm going to put into that system by spreading it over time through an all-pass system, that allows me to send that information with preserving its magnitude appropriately, without introducing nonlinear effects. So let's say, again, voice is pretty impulsive as I speak. I run it through the scrambler, which is a all-pass filter. Does not do any attenuation, but it spreads my voice over time. I send that through a semi-linear or just a linear amplifier that is linear across a certain regime of amplitudes and frequencies. And then when I, on the other side, receive that information, I can put it back together again through an all-pass filter. Now, one of the things that come out, and this you can look at actually in the book, is that if you have a stable and if you want a stable and causal all-pass system, then the group delay is going to be positive for all frequencies. And if you look at the argument or the phase for that all-pass system, it's always going to be negative. Okay? And then you can see in the book. I'll get back to you with the derivation of the all-pass system. This is, I don't know. I'm not sure what happened there. The next thing we're going to talk about on Friday, after we talk about the project and we talk about lab number 4, which we're going to post, we're going to talk about minimum phase systems. Okay? And minimum phase systems are very, very interesting systems because this is a certain situation in which you have a stable causal system that has an inverse or a perfect inverse, which is also stable and causal, which is not the case in general. Okay, so there's very, very unique type of systems and also very useful. Okay, with that, we'll see you on. Good luck tonight, and then I'll see you on Friday. Yeah.
I don't know what happened with the derivation. So if these two terms would be the same, then we could cancel them. But what effectively happens is that this is like plus minus x minus plus x. And that's why we get minus 2x. So this...
So if they were exactly the same, they'll cancel, right?
Yeah.
Oh,
so this is actually the conjugate.
Right.
So this is going to have, if this would have phase x, this would have phase minus x. Because this is in the numerator, we add minus x, then we subtract plus x.
Right. Okay. Yeah, thanks. Yeah, that was stupid. But this should have been plus here.
Yeah, this should be a plus. So it should not be the same as the denominator.
Right. Yeah. Hey, John, when is the midterm? April 4th.
I couldn't find it.
Oh, really? It's not posted?
I think it was announced in class.
Oh, can you put it on the website? Thanks.
We're still on the mic.